sklearnmulticlass. Description: multiclass classification is a type of supervised learning where the goal is to predict the class label of a data point from a set of more than two classes. In contrast to binary classification, where the model needs to distinguish between two classes, multiclass classification tackles the challenge of categorizing data into multiple distinct classes. Inputs: data. This refers to the input features used for training and predicting the class labels. It can be a tabular dataset with numerical and categorical features, or a dataset of images, text, or other types of data. The features should be carefully chosen to provide sufficient information for the model to distinguish between the different classes. Target: this represents the true class labels corresponding to each data point. It's a set of labels belonging to different categories, typically represented as categorical or numerical values. For example, if classifying different types of animals, the target could be dog, cat, bird, etc. Outputs: predictions. The model's output, representing the predicted class labels for new data points. It can be a numerical array, a list of class names, or probability scores for each class. Model: the trained model itself, which can be used for making predictions on new data. This is essential for deploying the model and using it for future classification tasks. Steps: data preparation. This involves cleaning, pre-processing, and transforming the data to make it suitable for the chosen classification model. This can include handling missing values, converting categorical variables to numerical values, and scaling numerical features. Model selection: there are various multiclass classification algorithms available in scikit-learn, each with its own strengths and weaknesses. Examples include logistic regression, support vector machines (SVM), decision trees, random forests, naive Bayes, and more. Choosing the right model depends on the nature of the data, the desired performance, and computational resources. Model training: the chosen model is trained on the prepared data, aiming to learn the relationship between the features and the target class labels. This process involves finding optimal model parameters that minimize the difference between predicted and actual labels. Model evaluation: the trained model's performance is assessed using appropriate evaluation metrics, such as accuracy, precision, recall, F1 score, and confusion matrix. This helps understand the model's effectiveness in classifying different classes and identify areas for improvement. Model deployment: once satisfied with the model's performance, it can be deployed for making predictions on new, unseen data. Metrics: accuracy: this measures the overall proportion of correctly classified samples. It's calculated as the ratio of correct predictions to the total number of predictions. Precision: this measures the proportion of correctly predicted positive samples among all samples predicted as positive. It's useful for evaluating models that aim to minimize false positives. Recall: this measures the proportion of correctly predicted positive samples among all actual positive samples. It's useful for evaluating models that aim to minimize false negatives. F1 score: this metric combines precision and recall into a single value, providing a balanced measure of a model's performance. It's especially useful when dealing with imbalanced datasets. Confusion matrix: this visualizes the performance of a classification model by showing the number of true positives, true negatives, false positives, and false negatives for each class. It helps to understand the model's strengths and weaknesses in classifying different classes. Visualization plots: confusion matrix plot: this visualizes the performance of a classification model by showing a number of true positives, true negatives, false positives, and false negatives for each class. It helps to understand the model's strengths and weaknesses in classifying different classes. ROC curve. This plots the true positive rate against the false positive rate for different classification thresholds. It helps to visualize the trade-off between sensitivity and specificity of the model. Precision recall curve. This plots the precision against the recall for different classification thresholds. It helps to visualize the trade-off between minimizing false positives and minimizing false negatives. Fine-tune parameters. Regularization parameter. This controls the strength of regularization, which helps prevent overfitting by penalizing complex models. Regularization techniques like L1 or L2 can be used to simplify the model and improve its generalization performance. Learning rate. This controls the step size taken during the optimization process. A smaller learning rate can lead to slower convergence but potentially a better solution. Number of trees in ensemble methods like random forests. This parameter determines the number of decision trees used in the ensemble. Increasing the number of trees can improve the model's accuracy but may also increase computational complexity. Uncertainty methods. Confidence scores. These are probabilities assigned by the model to each class for a given data point. Higher confidence scores indicate a higher probability of the predicted class being correct. Prediction intervals. These provide a range of values around the predicted class, indicating the model's uncertainty about the prediction. Wider intervals suggest higher uncertainty. Challenges and fixes. Challenge 1. Overfitting. This happens when the model learns the training data too well and fails to generalize to new data. Sample use case that resulted in challenge 1. A model trained on a small dataset with many features may overfit, resulting in poor performance on unseen data. Fixes to challenge 1. Use regularization techniques, such as L1 or L2 regularization, to penalize complex models. Employ cross-validation to evaluate the model's performance on unseen data. Consider reducing the number of features or using feature selection techniques to simplify a model. Challenge 2. Imbalanced dataset. This occurs when the classes in the training data are not represented equally, leading to biased models that favor the majority class. Sample use case that resulted in challenge 2. A dataset with a large number of examples from one class and only a few examples from another class will lead to a model that is more likely to predict the majority class. Fixes to challenge 2. Use techniques like oversampling, undersampling, or synthetic minority oversampling techniques to balance the dataset. Consider using class weights in the model to give more importance to the minority class. Evaluate the model using appropriate metrics, such as F1 score, that are less sensitive to class imbalance. Challenge 3. High dimensionality. This arises when the number of features in the data is very large, leading to computational challenges and potentially overfitting. Sample use case that resulted in challenge 3. A dataset with thousands of features may be difficult to process and can lead to a model that is overly complex and prone to overfitting. Fixes to challenge 3. Use dimensionality reduction techniques, such as principal component analysis (PCA) or linear discriminant analysis (LDA), to reduce the number of features while preserving important information. Employ feature selection techniques to identify and select the most relevant features for a classification task. Challenge 4. Data sparsity. This occurs when there are many missing values in the data, leading to inaccurate models or unreliable predictions. Sample use case that resulted in challenge 4. A dataset with many missing values for certain Features will make it difficult for the model to learn patterns and make accurate predictions. Fixes to challenge 4. Impute missing values using techniques like mean imputation, median imputation, or k-nearest neighbors imputation. Use models that are robust to missing values, such as decision trees or random forests. Challenge 5. Interpretability. Some multi-class classification models, such as neural networks, can be difficult to interpret. Sample use case that resulted in challenge 5. A neural network with many layers and hidden units can be difficult to understand, making it challenging to explain the model's predictions. Fixes to challenge 5. Use techniques like feature importance analysis to understand which features are most influential in the model's predictions. Employ model simplification techniques, such as pruning or reducing the complexity of the model. To improve interpretability, consider using interpretable models, such as decision trees or rule-based models, which are easier to understand.